Let us talk about Radix Sort algorithm. Radix Sort algorithm, like counting sort, is also a linear time algorithm if your data is within a limited range. Now we already have counting sort. Why do we need another sorting algorithm? The reason is counting sort will take time big O of n plus k, where k is the range of elements. And if k is n square, then counting sort will take n square, which is worse than standard comparison-based algorithms like merge sort and heap sort. Radix sort is a sorting algorithm that supports linear time even for a larger range. It works in linear time even if your data is in range from 0 to n square or 0 to n cube. It uses counting sort as a subroutine to sort the elements. And like counting sort, it's not a comparison-based algorithm, because if you have a normal comparison-based algorithm, then you cannot sort the elements in time complexity less than n log n. And this is an algorithm that sorts the elements in linear time if they are in small range. Let's now see the working of Radix sort algorithm. Let's say we have these elements, we want to sort them in increasing order. So first thing is, we'll make sure that all the numbers have same number of digits. And how many digits every number should have? It should be equal to the number of digits in the largest number. So the largest number is 319 and it has 3 digits. Now how do you find out largest number in an array? You can simply traverse through the array and find the maximum element in linear time. And how do you find out number of digits in the largest number? You can use logarithmic, right? You can take the log in base 10. So you figure out there are 3 digits in the largest number. So what you do is, you consider that even the single digit and double digit numbers have a 0 appended to them at the beginning, right? For understanding of the algorithm. So I've rewritten the array with zeros appended at the beginning or pre-appended at the beginning, right? After we attach zeros, we have now all the numbers with same number of digits. What we are going to do now is, since every number is a 3-digit number, we are going to do 3 passes. In the first pass, we are going to sort all the numbers. We are going to use a stable sort. Basically, we are going to use counting sort to sort all the numbers according to the last digit. Then we are going to sort all the numbers according to the middle digit. Then we are going to sort all the numbers according to the first digit. Suppose we had 4-digit numbers. In that case, we would require 4 passes. So let's see what happens when you run the first pass. What are the last digits? 0, 0, 8, 6, 2, 9. And you want to sort them in a stable way, right? So which number will come first? 100, because it has the smallest digit value and it appears with this number before this number, right? It also has the smallest value, but this appears first. So we write 100 first, then we write 0450, and after that 212, then 006, then 008, then 319. You can notice that we have all the numbers now sorted according to the last digit. This has the smallest last digit, then this also has the smallest last digit, then 2, then 6, then 8, then 9. Now we sort these numbers according to middle digit, and again we do a stable sort. So which numbers have the smallest middle digit? These 3 numbers, right? These 3 numbers have the smallest middle digit. So we'll put these 3 numbers in the same order as they appear in the input, because we are doing a stable sort. 100 appears first, then 006, then 008. Now we put 212 because 1 is greater than 0, right? Now we put 319 because this one is also greater than 0. So these 2 numbers have the same middle digit, but 212 appeared first, so we are putting 212 first. Now we put 050 at the end. This has the highest middle digit. And after sorting according to middle digit, we sort according to the most significant digit or first digit. And after you stable sort according to the first digit, you get these numbers. And you can notice that your input is sorted. We got the sorted array. Now please pause this video and try to write down an implementation of this approach. Please note that we are going to use counting sort as a subroutine to sort numbers according to individual digits, and we are simply going to call counting sort for all the digits. Let us see the implementation of Radix Sort. This Radix Sort function can be divided into 2 sections. The first section finds out the maximum element in the array. It's a very simple logic where we initialize maximum as array 0 we compare it with all the other elements, and if an element is greater, we update the maximum. The second section of this Radix sort function calls counting sort for every digit in the maximum number. So we have a variable called exp. This exp represents a power of 10. We initialize it as 10 raised to the power 0, then we go to 10 raised to the power 1, 10 raised to the power 2, 10 raised to the power 3, and so on. We keep incrementing the power while mx divided by exp is greater than 0. So if your maximum number mx is 319, then how many times this loop will run? This loop will run for exp equal to 1. This will run for exp equal to 10. Then it will run for exp equal to 100. It will not run for exp equal to 1000, because when exp becomes 1000, 319 divided by 1000 will be 0. So that's the logic we have implemented here. We have an exp variable which is a power of 10, and we run this loop only equal to the number of digits in your maximum number. So if we consider this example, our mx is going to be 319. Then we are going to run a loop, and inside this loop we are going to call counting sort first with exp equal to 1, then exp equal to 10, and then exp equal to 100. So this is all we do in the Radix sort. Now comes the counting sort part. The counting sort code that we have written here, it is similar to the counting sort implementation that we discussed in the counting sort video. The only difference we have in this implementation is, instead of using array I directly as an index, we use array I divided by exp modulo 10 as an index. Now if you do some mathematics using pen and paper, you can notice that if exp is 1, then this expression will give you the last digit of array I. If exp is 10, then this expression will give you the second last digit of array I. And if exp is 100, then third last digit of array I. Let's see how. Say exp is 1, then what you will do? You will divide array I by 1, which means array I only, and array I modulo 10 gives you the last digit. Now say exp is 10, then you will divide array I by exp, which means your last digit will go off, right? For example, if array I is 319, if you divide by 10, what you will get? You will get 31. And if you do 31 modulo 10, you will get 1, which is your second last digit. So these expressions here give you the digit according to value of exp. When exp is 1, it gives you the last digit. When exp is 10, it gives you the second last digit. When exp is 100, it gives you the third last digit. And the rest of the logic is exactly same as counting sort. We are making a count array, then we are making an output array, and we are filling this output array using the expressions here. Let's now see the step-by-step working for this particular example. So this is our example. Our first step is to find the maximum element mx, which is 319. Now we are going to run a loop, and inside this loop we are going to call counting sort 3 times with arr. Size of array is 6. So this 6 value is actually n is 6, and exp is 1 in this call. In this call, n is again 6 and exp is 10. Here n is 6 and exp is 100. Right? So these 3 calls we make inside this loop for exp equal to 1, exp equal to 10, and exp equal to 100. Now for this call, what we do is we sort the numbers according to the last digit, because exp is 10. And this is same counting sort logic. It is strongly recommended that you see the counting sort video first. And if you've not seen now, then you can refer this counting sort video now, and you will get the idea how does this code work. So first thing that we do in this counting sort algorithm is we make a count array, right? And we initialize this array as 0. Now what we do, we traverse through our input array and we fill the counts of individual elements according to the current digit. So current digit is 1 that we are considering because exp is 1 at this moment. So how many numbers we have as last digit as 0? So we have 2 numbers, 150. That's why we have count of 0 as 2. Then we have no number with last digit as 1. Then we have 1 number with last digit as 2. So the count is 1. Now we do not have any numbers whose last digits are 3, 4, 5. Then we have a number where last digit is 6. And the number is this 6. Then we have one more number with last digit as 8, this number. Then we have one number with last digit as 9, which is 319. So we built our count array. Now we do a cumulative sum in this count array in this particular step, right? And this is all part of counting sort. And cumulative sum we do to get the last position where this particular element should be put, right? So if you see this count array, you can notice that the element with last digit at 9 should be put at position 6. The element with last digit as 8 should be put at position 5. And the element with last digit as 6 should be put at position 4. And the elements, there are multiple elements with last digit as 0. The last occurrence of such an element should be put at position 2. Position 2 means index 1, right? So we build this count array, and using this count array, we fill our output array, right? We find out the positions of every element using this count array. We subtract 1 from this position to find out the index, and we put those elements at those indexes. And then we increment the count so that if there are multiple occurrences of a digit, for next occurrence, we get the correct position. So this is what is done in this part, and we have the correct output array. Then we copy this output array to original array. So our original array becomes this. And then when we call counting sort 610, our original array changes to this. Now this array is sorted according to second digit. First time we sort according to first digit or last digit. Then we sort according to the second last digit. Then we sort according to the third last digit or the most significant digit, and we finally get our sorted output. Let us now talk about time complexity of Radix sort. So first step of this algorithm takes theta n time because we are simply finding the maximum in an array of size n. Now the second step, it runs for every digit in the maximum number. Let's say there are d digits in your maximum number. Then inside this loop, we call counting sort, right? How much time counting sort takes? If you have n numbers and these numbers are in range from 0 to k minus 1, then counting sort takes theta of n plus k time. Now here we have n numbers and range of these numbers is greater. It's not actually from 0 to a small number k minus 1. Here we have a larger range, but what we are going to do, we are going to sort these numbers according to a particular digit. And these digits are in range from 0 to 9. So we have actually k as 10 in this counting sort. In general, if the numbers are in base b, then we can say it's going to take theta n plus b time. And in this particular implementation, b is actually 10. So this step takes theta n plus b, and here in this example, our b is 10, base is 10. So this is the overall time complexity of Radix sort. It's theta n. So we can ignore theta n because this part is anyways n multiplied by something. So we can say that overall time complexity of this Radix sort implementation is this much, which is this part. Here is an interesting fact about Radix sort. If you increase the value of base b, for example, if you increase from 10 to 20, then this loop will run less number of times. Then your d will decrease, right? Because you will have less number of digits in a bigger base. Now what will change? Your extra space required by the counting sort will increase. Here we need extra space of size 10, but if you're using a bigger base, then that size will increase. So this is an interesting trade-off between space and time in the implementation of Radix sort. If we want to reduce the time, we can increase the base, right? And then this d value will decrease because it's in multiplication, but your extra space required will increase. Let us now see extra space required by Radix sort. So it requires this much time, and it requires theta of n plus b extra space. This much extra space is required by the counting sort implementation, and it is using counting sort, so it's going to need this much extra space. So this much extra space and this much time required by counting sort, Radix sort algorithm here that we discussed. So Radix sort is an algorithm that works better than counting sort if your range is bigger than linear. It uses counting sort as a routine, and it's a stable algorithm because counting sort stable is used, and if you have two numbers, say 100 and 100, then they'll be remained in their original order, right? The first 100 will remain at the first position because for every digit we are using a stable count sort.